Hello everyone, I hope you're all doing well. So in today's video, I'll be going through the 2021 physics exam for the Northern Hemisphere multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. A wire carrying a current of 6 amp passes through a magnetic field B of strength this, as shown below. The magnetic field is exactly 1 meter wide. Okay. The magnitude of the force on the wire is closest to what? It's actually 0 because the magnetic field and the current direction are both parallel. They need to be perpendicular for a force to be created. So this has to be 0. Remember, if both are parallel, there is no force going to be produced. Nice and easy. Question 2. 3 charges negative Q this are placed in the vertices of an equilateral triangle as shown. Actually, this question looks like similar to the 2019 exam multiple choice section. Which of the following arrows best represents the direction of the net force on the charge negative Q? Nice. Let's do it. So let's put a color. So let's have a look at that negative Q. Imagine you're that negative Q. And so let's be this negative Q. Let's look at the first effect between these two charges. Well, they're both this one's negative and this is positive, so there's going to be an attractive force. So negative Q is actually going to be attracted to it. That's what we know. Now let's have a look at negative Q and positive 2Q. Again, negative Q is also going to be attracted because that's a positive charge and negative Q is negative. So it's going to be this. So what we have right now is actually the, sum of two forces. What we need to find is the actual net force of these two sums. And how do we do that? Easy. Put them, if I put this right over here, as you can see, the total sum, so the net force of these two forces is going to be a straight line downwards. Pretty much. So B looks like your answer. Nice and easy. Very, very similar to the it's actually the same. It's the same question from the 2019, but they've just changed these two charges, I believe so. So yeah. Nice question. All right, let's move on to the next question. Question 3. A 45-gram golf ball, initially at rest, is hit by a golf club. The contact time between the club and the ball is 0.5 milliseconds. The magnitude of the final velocity of the ball is 41 meters per second. Which of the following is closest to the average force experienced by the golf ball? Easy. Now we know. Actually, this is also some similar to one of the exam questions from VCA. They always start to repeat exam questions, which, it's easy. So we know that impulse is equal to the change in momentum. And we also know impulse is equal to force, the average force times time. So we want to find this force over here, but we do luckily have also time, but we just need to find the impulse. But we know impulse is equal to this over here, so we can actually replace this part with that. mv minus u. Done. And so divide both sides by t to get rid of that t, and this formula will give us our force. Let's put that into our calculator. So mass, what's the mass of the golf ball? Well, remember it's in grams, so make sure it's in kilograms. So divided by 1,000, that gives me 0.045 kilograms. V is your final velocity, and we know the final velocity is 41 meters per second minus your initial, which was at rest, so minus 0. All being divided by the time. And be careful, the time is a millisecond, so you need to convert it to seconds. Which is 0.5 times 10 to the power milli, means to the negative 3. Put that in your calculator and you should get your force. Let's do that. 0.045, 41, 0.50 times 10 to the negative 3. And that gives me 3,690, which is approximately 3.7 kilonewtons. Done. Easy. Next question. Question 4. A person has a mass of 60 kilograms. Which of the following is closest to the weight of this person on the Earth's surface? Look at the word weight. A lot of people make this, wrong mistake of saying that weight is like your mass. They're comparing it like you weigh 20 kilograms. No, weight is a force. It's the actual force of gravity. Your mass is 60 kilograms, not your weight. So Your weight is a force. So having a look at the answers, there's some in kilograms, so take those out. And so we know that weight is just the force of gravity, which is mg. What's the mass? It's actually 60 times in the Earth stuff, it's g is 9.8, and that's going to give you your force. So times 9.8, 588 newtons, which is D. Let's do a different color, a little bit green. Question 5. When a spacecraft orbits Earth, its orbital period is not a function of what? So what we have here is, let's just draw. Alright, oops, that's ugly. So imagine we had a little, and let's say this is Earth right over here. And say we have a spacecraft orbiting, actually, just like a something orbiting. Yep, and say this is your spacecraft right over here. Now, alright, and which one? So when the spacecraft orbits the Earth, its orbital period is not a function of what? So have a look at your formulas, actually, and so which formulas uses period? Well, I'm having a look over mine, just going to my summary sheet. So let's look at the first one, the mass of the Earth. Well, we actually do need the mass of the Earth. It does affect the period, because remember, by Kepler's law, this formula over here, T squared is equal to gm over 4 pi squared. So all these quantities over here affect the period, because it's in that formula. It's the actual function of that formula. So what I'm thinking here is, okay, it says the mass of the Earth. Remember, this is your big M, not your little m. So this is your mass of the Earth, which is this big M. This is little m right here. So yes, the mass of the Earth is a function of the orbital period. So that's wrong. B, the mass of the spacecraft, not true. I can't see in anywhere here that the mass of the spacecraft, is really used to calculate the period. It's not an actual function. So that's what I would say that I put a question mark, which looks wrong, to be honest. C, velocity of the spacecraft. Yeah, no, velocity of the spacecraft from this formula, V is equal to 2 pi r over t. Remember, t is your period. It is a function of velocity, so that's also wrong. D, height of the spacecraft above the Earth. So the height of the, which is just plusing your radius, that's your r value, and it is a function of period. So also that's wrong. So B is wrong. So this is the main important thing. Your actual mass of the spacecraft doesn't really affect the orbital period. So you can have like a bigger mass. So you have a planet orbiting Earth, and it will still have the same orbital period. It really does not. It's not about the mass of the spacecraft. Question 6. The mains voltage in a particular part of Australia is AC with a voltage of 240 RMS, whichever following is closer to the peak-to-peak voltage for the main voltage. Easy. You should know these formulas in your summary sheet. We know if we want to go from the peak to peak, like from RMS to peak, it's actually 2 times the root of 2 volts RMS. This is the formula, so it's just 2 root 2. What's our voltage in RMS? It's 240 volts. Putting that in our calculator gives me 678, which looks like the closest is D. Nice. Question 7. Electrical power stations are often situated far from cities that require the power that they generate. Which of the following best describes the reason for the high voltage transmission over the electrical energy? Easy. This is one of the most easiest questions. This is what you should guys know. What do we know? Let's have a draw at the diagram here. We know for a fact. Let me draw. So we know, say imagine this is your power supply. Let's say this is like, a big power supply that supplies all the houses. It's very far, of course, the power stations. So this is your power station. And so what we have is we always have a step-up transformer. And imagine this resistor is your transmission lines. Imagine how long those transmission lines are. Of course, the longer they are, we have a high resistance. So imagine this is your, and of course, we're going to draw another transformer. This is your step-down transformer. And imagine this is your house. I'm just going to draw it as a light globe. This is like the most typical case in VCE that you use. And let's have a look here. So this here is your step up. So I'm going to write voltage up. Oh, no, actually, just step up. T up. This is T down. You're probably like, why do we step it up? For like, let's say it's low voltage to high voltage in those transmission line. Why do we do that? Remember, we are trying to decrease the power loss in those transmission lines. Unfortunately, there's actually a lot of power loss in those transmission lines. And how do we decrease that? From this formula, you should know. P is equal to I squared over R. Remember, the resistance is constant of this transmission line. So the only way that we can decrease this power loss is by changing the current. And remember, if you put a step-up transformer here, meaning that we have so imagine a low voltage here, and we step it up to a high voltage in this transmission line, we have a very high voltage. What do we know about high voltage? We have a low current. There's this inverse proportionality. You have a high voltage, it means you have a low current. So because we put high voltage in these transmission lines, we have a low current in those transmission lines. We've decreased this current, and meaning that, putting this in your formula, if we decrease the current, we've actually decreased the power loss in those transmission lines. And that's the great thing that we do, that we try to do in the so we don't lose power. That's the main reason why we use high voltage in those transmission electrical. So that's why in those transmissions lines, we put high voltage. Easy. Let's have a look at the answers. A. Transformers can be used to increase the voltage in the cities. I mean, yeah, but when we're in the cities, like these close to the cities, the houses and stuff, we try to step it down, the voltage. We don't want to step it up, so that's wrong. Transformation can be used to increase the voltage in the cities. Yes, it can, but we try to decrease the, we try to step down the voltage. Yeah. So that's not right, and that doesn't explain why high voltage transmission of electrical energy. B. High voltages reduce the energy losses in the transmission line. Yes, this is the reason. Using high voltage means low current. Low current means less energy is lost, so less power. So it looks right. C. High voltages provide large current. No, high voltages provide small current, less current. Currents needed for efficient transmission? No, we want only low current. So that's just rubbish already. So C is also rubbish. D. High voltages can reduce the overall resistance in the transmission. No, the resistance is constant. So I wouldn't, using a high voltage doesn't really affect that. So the only answer is B. That actually does explain. Whatever we explain, B explains it better. So B explains that. Let's have a look at 8. Let's use a different color. Okay, in the diagram below, the solid line represents the graph of the output EMF versus time produced by an AC generator. A single change is made to this AC generator and its operation, and the new graph of its output versus time is shown in the dashed lines. Okay, so what can we see? So it was originally this, and then its amplitude double, and also the period half. So it's double amplitude, and the period looks like it's been halved. So this is your period, one cycle for a period, and now it's actually halved. All right, let's have a look at these. Which of the following best describes the change made to this AC generator? Let's look at the first one. The area of the coil was doubled. Wrong. Why? So remember, EMF is equal to negative n change in flux over change in time. If you double the area, meaning that you double the flux, it will increase the amplitude of the EMF, which it has done. As you can see, it's doubled the amplitude. But the problem is, why is the period still halved? Why is it still halved? Yeah, so if they've only doubled the coil, it would have just looked like this. It still would have had the same period, but with a double amplitude. Would have just had a double amplitude, so that's not right. B. The speed of the rotation was halved. If you actually half the rotation speed, so imagine you slow it down, it will take twice the amount, so double the period. And remember, that's wrong because the period was actually halved. We don't want to double that period. C. The speed of the rotation was the speed of the rotation was doubled. So if you speed it up, it will take half the time. So the period actually has been halved, which is good. That looks good. But let's actually see if that affects the amplitude. Does it double the amplitude? And let's see. If you half the period, which is halving the time here, you put half the time. That doubles. So if you put a half here, the time, it actually doubles your EMF amplitude, which is great, and that also makes sense. So C looks great. C explains all of that. Let's have a look at the next one. The number of turns of the wire in the coil will double. Again, if you double this, it will increase the amplitude, but wouldn't increase the period. So that's also wrong. So choose C. Question 9. The diagram below shows a bar magnet moving upwards in a coil. Just having a look at this diagram, it looks like Lenz's law. Which of the following correctly identifies the direction of the induced current as viewed from the top of the coil, so from the top, and the direction of the magnetic field produced by the induced current. So we're talking about the induced magnetic field inside that coil. All right, let's have a look. So what we're doing is we're putting this north pole inwards. So what's happening? So the magnetic field is actually going up. So what do we know? So we know that the magnetic flux through the loop is actually increasing because the magnetic field lines are going inside. And it's actually increasing upwards. So we can, like we said, the magnetic flux through the loop is increasing up. But by Lenz's law, we know by Lenz's law, the induced magnetic field will oppose this change in flux. So it will actually be directed downwards. So you know how this is going upwards? It will try to repel it by Lenz's law. And it will be a downwards. This here will have a downwards magnetic flux. It will have an induced magnetic field that will be pointed downwards to oppose that change in flux. And yeah, so this here, so we know for a fact that our induced magnetic field is actually going to be acting downwards. Finally, look at this magnetic field lines. Yeah, magnetic field direction is going to be downwards, so not these two, because this is saying upwards. And also have a look at what current direction. Okay, so using the right hand coil rule, the induced current will flow clockwise, because remember, imagine holding your hand in like a in a coil, and so like another right hand grip rule. Use the right hand grip rule, and your thumb is going to be acting to the direction of the magnetic field, the induced magnetic field, which is downwards. So imagine putting your hand downwards and looking through the top. Is it going to be acting clockwise or anti-clockwise? Your hands are curling. Well, my hands are curling in the clockwise direction. So your induced current is going to be acting clockwise, which is this way. So choose A. Easy. Question 10 and 11. Let's have a look at this. Melissa launches a ball from a height h above the ground at a speed of 8 meters per second at an angle of 30 degrees above the horizontal. The time of the ball flight is 1 second. The diagram below shows the trajectory of the ball. Ignoring air resistance, whichever following is closest to the horizontal distance that the ball landed from Melissa. So we're trying to calculate this horizontal distance. This distance. What do we know about the horizontal distance? The only formula that you remember that the velocity is always constant throughout the horizontal. So remember, always the velocity is constant. It doesn't change. There is no acceleration. We know that in the horizontal direction, the velocity is constant throughout its motion. So looking at the horizontal direction, you know the formula that we only use is distance is equal to v times t. That's the only formula that you should be using when you're doing calculations in the horizontal direction through projectile equations. Whenever you're doing vertical, then you have to use through that. But yeah, and so what we're trying to calculate is the distance, and we just want the velocity. Now, easy. The velocity is, because we know it's constant throughout its motion, we just need to find the velocity in the horizontal direction, which is what? This is a right angle triangle. And remember, so using your trigonometric ratios, it's just going to be 8 cos 30 degrees. Remember, so this is what we want. This here is our speed, our velocity, this part in the horizontal direction. So remember, this is your hypotenuse, this is your adjacent. So this is going to be a cos, and it's going to be 30, and yeah. So now we have our velocity, which is always constant throughout its motion, times the time it takes for the ball to reach. They said it's 1 second, so yeah. So putting that, and that should give you your distance, your horizontal distance. What a nice, beautiful question. Which is 6.93. So it looks like C is your answer for that one. Question 11. Which of the following diagram best shows the direction of the resultant force on the ball at the position of the maximum height in real situations where air resistance is not ignored? So we actually have air resistance. Let's have a look here. So if it's at its maximum height, what do we know? Well, we know that there's always a force of gravity that's going to be acting downwards. So force of gravity. And also, because, air resistance, as you throw the ball, there is air resistance. It's going to try to oppose that motion. So it's going to have an air resistance this way, right over this way. And that, you remember, as you're throwing the ball, air is going to try to oppose that motion. And yeah, so we have this, and we just need to find the resultant force. So putting these two together, so bring this right over here. What is the triangle that's been formed? It's an actual, it's this over here. So it's going to be looking like it's going to be downwards. So this is your resultant direction, resultant force. Which one looks like that? It looks like D is your answer. See, this one's horizontally down. This one's right. This one's left. This one's at an angle. Like we said, it is at an angle. So it looks like D is your answer. Easy. Question 12. A mass at the end of an ideal spring is oscillating freely up and down. Which of the following best describes the motion of the oscillating mass? Which of if its speed is a minimum only at the top of the motion? Well, let's actually look at this. We know that the actual speed at the top of the motion is 0 because the kinetic energy is 0. So we can so what we say is speed is at its minimum at the top and at the bottom, because when it goes downwards, it's gonna like stop the speed, and also at the bottom, it's also a minimum, the way the kinetic energy is 0. So you're probably asking, where is the speed the most maximum? It's in the middle. It's at its equilibrium position, and that's where your speed is at its maximum. You should know this. This is very important, especially in the exam questions in these days. They've been putting a lot of spring questions, and yeah. So we know that the speed, so the kinetic energy, of course, at the top of this motion is always, so kinetic energy is 0. And also kinetic energy at the bottom is 0. And so kinetic energy here is at its max, and that's why we have maximum velocity there. Done. So its speed is at its minimum only at the top of its motion? No, it's at the minimum at both the top and the bottom, so that's wrong. B, its speed is at its maximum when its acceleration is at its maximum. We know that the acceleration is at so we know that the acceleration is actually, what color should I use this? We know that the acceleration is at 0 in the equilibrium position. And so the actual acceleration is at its maximum at the bottom and at the top. And think of it, like when you're oscillating up and down, when it's at its down position like this over here, it wants to accelerate upwards. It wants to go upwards. And when it's at the top position, it wants to go downwards. It wants to accelerate downwards. So that's why it oscillates. So its speed is at maximum when its acceleration is at so the acceleration is at its maximum when that's wrong. The speed's at so its speed is maximum, which is in the equilibrium position, when its acceleration is at maximum. No, acceleration is 0 at its maximum speed, so that's also wrong. C, its acceleration has a minimum value at both the top and the bottom of the motion. Wrong. So the acceleration is at its maximum at the top and at the bottom. D, its acceleration has a maximum value upwards when the mass is stationary at the bottom. That's true, because here is when it's at the bottom and it's stationary. It wants to go, so the acceleration is at its maximum and it wants to go upwards. Its direction is upwards. So D looks great. 13. Joanna is an observer in spaceship P and is wearing spaceship Q fly past at a relative speed of this. She observed a stationary clock measuring a time interval of 75 seconds between two events in spaceship Q. This is the proper time interval. Okay, we have the proper time. Great. which of the following is closest to the time interval observed between the two events in spaceship's P frame of reference? So in spaceship's P frame of reference, it's going to be time dilated. The time's actually going to be dilated, and that's what we want to calculate. Okay, easy. So we know that for time dilation, when we calculate time dilation, it's actually just T equals proper time times your Lorentz factor. So what's our proper time? It is just 75 seconds times your Lorentz factor, which is 3. Easy. And that gives me 225 seconds, which is D. Nice. Question 14. The diagram below represents a standing wave. The point P on the standing wave is what? A node? Well, let's have a look. P here. We know this is where a node is going to happen. This is, by the way, when it's always here, these are all nodes. These points here are all nodes where destructive interference occurs. These parts here on top are actually called antinodes. They're where constructive interference occurs. So at P is a node, and it's where destructive interference occurs, which looks like a node resulting from destructive interference. Great. That's what a node is. Done. Question 15. The polarization of light supports what? Okay, what is polarization of light? Polarization, again, is it's wave. It only occurs for transverse waves, by the way. And yeah, so the polarization of light supports the wave model, the particle model, or both, or neither. Well, it only supports the wave model because it only works for it supports like so polarization only occurs for transverse waves, which actually just supports the wave model because they're waves. So yeah, why would it support the particle model? So it's just A. That's quite nice and easy. Remember, polarization of light, it only occurs for transverse waves. And yeah, nice. Question 16. A red laser used in a double slit experiment creates an interference pattern on a screen as shown below. This question, just having a look at it, I know for a fact what's going to ask me. The most repeated question in every exam, and it's the easiest way to get marks. The red laser is replaced with a green laser. So what's happened here? So a red laser has a high frequency, has a low frequency, and they've replaced it with a green laser, which actually has a higher frequency. And remember, if you have a high frequency, it means you have a low, remember, it's inversely proportional. You have a low wavelength. So if you have a low frequency, you have a high wavelength. So what we've done is we've actually just decreased the wavelength. Which of the following best explains what happens to the spacing between the adjacent bright bands when the green light is used? Easy. So the formula that should come up in your mind is that change in x, the space, spacing, is equal to this, where we've actually just decreased the wavelength. So if we decrease this wavelength, it will decrease that spacing between those bright bands, and hence easy. B is your answer. One of the most easiest and nicest question to get marks for. Yeah. 17. Protons of mass 1.6 blah 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 are accelerated to a speed of this. The best estimate of the de Broglie wavelength of these protons is what? A nice also question. So we know that de Broglie is h over mc. And yeah, putting this all into our formula, we know h is 6.63 times 10 to the power of negative 34 all over the mass of the proton, which is 1.67 times 10 to the power of negative 27, and the speed, which is 2.0 times 10 to the power of 3. And that's it. So putting that all in our calculator gives us it gives me 1.98 times 10 to the negative 10, which is approximately B. Yep, is that right? Yes, it looks good. Question 18. Experiments on the photoelectrical effect involve shining lights on a metal surface. Measurements are made on the number of emitted electrons and the maximum kinetic energy from the metal surface. This is done for different, frequencies and intensities of light. Which of the following statements would not be one of the experimental findings? One of the most nicest and easiest question. You know that through the photoelectrical effect, intensity only increases the number of electrons, the photoelectrons, And that's what it only affects. It doesn't affect the kinetic energy, just remember, it doesn't do anything of that. Whereas the frequency affects the kinetic energy, but doesn't affect the number of kinetic energy. So yeah, it's very, whenever you do photoelectric effect, it's one of the most nicest questions to get. Let's have a look at the question. Wait. Which of the following statements would not be one of the experimental findings? Okay, so we're trying to find which one's wrong. The ability to eject electrons from this metal dependent on only the frequency of light. True. So for us to eject electrons, we must, put a frequency above the threshold frequency. If we go above and beyond the threshold frequency, we are able to eject those electrons. So yeah, it is dependent on the frequency of light. So that's correct. So it's wrong because we want which one's wrong. B, the stopping potential or the stopping voltage for the photoelectrons was independent on the light intensity. Correct. It is independent on the light intensity. It only depends on the frequency, the stopping voltage. C, the maximum kinetic energy of photoelectrons depended only on light intensity. Wrong. Remember, the maximum kinetic energy of photoelectrons is only dependent on the frequency, not the light intensity. Here is wrong. They said dependent. So I would put C as our answer, but let's look at D also. At frequencies below the threshold frequency, no electrons were ejected from this metal, no matter how high the light intensity was. Beautiful. True. Yep, that looks good. So done. 19. In an experimental investigation, an independent variable is one that is what? So remember, your independent variable is the variable that you change, and it affects the dependent variable. Think of it as just maths. Y equals mx plus c. It's your independent variable, and this is your dependent variable. Whatever you do to the x, it will result in a change in y. So like if I shove in 2, y will be like 3. So it affects y. Whatever you do to x, it will affect y. And that's what it does. That's what an independent variable does. Let's have a look at the answers. Independent, so A, independent on the investigator's control. What? The investigator can control it because he can put any values he wants. He chooses what values to put. Like, for example, yeah, that's rubbish. It's dependent. So the investigator actually has control of that independent variable. In experimental investigation, an independent variable is one that is independent. Nope, so that was wrong. Okay, B. A value that is selected by the investigator. True, yeah. A value that is selected by Dre. Yes, the value. An investigator can actually choose values for it. As we said, you can put any values of x and it will result in y. So, looks good. Put a tick there. C. Fixed throughout the experiment. No, that's the control variable, not the independent variable. D. The key variable to be measured. No, the key variable that's measured is the y. It's your actual dependent variable. So the only answer is B. Beautiful. Let's have a look at the last question. A nucleus in an excited state emits a gamma ray of energy, which is this, as it decays to its ground state. The initial mass of the excited nucleus is M1, so Mi, which is the initial mass. The final mass of the nucleus after the decay is closest to what? Okay, so let's have a look. Let's just have a draw. Let's draw these two here. Straight lines. I don't know if it's oh my god, they're so ugly, but like that and like that. So imagine this here was your initial mass, Mi, and this is your final mass, because remember this is your energy high state, and it emits some gamma rays. So imagine it goes downwards, it emits, and it's gonna release some gamma rays, and it will have the final mass. Now there would have been some mass lost, of course, because the gamma rays, remember, E is equal to mc squared, where energy, in terms of this, is gamma rays, affects the mass. So there would have been some energy lost. In this case, what is that mass lost? Which is easy. We know that the energy that is being emitted is this much. So E is equal to c squared is equal to your mass. So your energy is 3.6 times 10 to the negative 13, all divided by c squared, which is the speed of light. 3.0 times 10 to the power of 8 squared. 0.6 times 10 to the negative 13. 3.0 times 10 to the power of 8 squared. And that emits, 4 times 10 to the power of negative 30 kilograms. So we had some initial mass, and we've lost this mass because energy was released, and we would have had our final mass. So your final mass, MF, is just your initial mass minus the energy, the mass lost, which is 4 times 10 to the power of negative 30, which looks like MI minus 4. Yes, A looks great. And that's it. That's it for this exam. I hope you guys learned something through this video, and yeah, try it out for yourself. Please make sure to like and subscribe, and have a great day, guys. Bye bye.